Hello everyone and welcome back to the StarSailor podcast with Peter Clark and Hannah Hutchins. Today we're releasing the next part of our interview with Professor Bill Keel of the University of Alabama, which we didn't quite get time to get fit into our 365 Days of Astronomy podcast on overlaps. So today we're beginning our interview on AGN.
First of all, what is an AGN and what makes them so interesting?
The original definition of an AGN was a region in the nucleus of a galaxy which has energy output in an amount or a kind that you can't account for with the ordinary processes of stars and star birth and star death. And by now, it seems clear that what all the different forms of AGN that we see observationally have in common is they're powered by accretion into a supermassive black hole. The enormously strong gravitational pull, the so-called deep potential well, heats material so that the natural energy emerging from material swirling around the black hole right before it has to fall in comes out in X-rays. So we see all sorts of excitement when these X-rays heat, ionize, and illuminate surrounding material so that you have extremely strong emission lines, very highly ionized gas, which make these stand out from ordinary, allegedly normal galaxies. And one of the things that really emerged only as a result of getting spectra with Hubble is the discovery that these supermassive black holes are ubiquitous in bright, massive galaxies. So the AGN phase is something that all bright, massive galaxies have gone through at various times in their lives. One way to think of it is the AGN is what we see when the black hole is growing. So that's good reason to think that this AGN phase is something that's important to the lives of all galaxies, not just the ones that we happen to see it on right now. So AGN are, as it turns out, an important part of understanding the development and evolution of galaxies.
When do AGN become less common in the universe?
At least for the bright, powerful AGN, we're in the enviable position, at least compared to our colleagues in archaeology or paleontology, that we can see what things were like in the past. As we look back through cosmic time, out in distance from us, we can see, for example, how many powerful quasars or how many powerful radio galaxies there were. And in both cases, we find that in cosmic time, they initially increased in number very rapidly until they went through a peak, so what sometimes people call the quasar epoch, about 2/3 of the way back through cosmic time. So that would be broadly 8 to 11 billion years ago, when the fraction of galaxies showing these extreme kinds of activity was about 1,000 times greater. And ever since that peak, a little more than redshift 2, for people who think in terms of Z variable, the fraction of galaxies with these power forms of activity has been decreasing, so that what we see around us is almost the dregs of this epoch of universal fireworks.
Some AGN are known to have jets. What are these and what causes them?
When we talk about jets from AGN, what we see is most often from radio emission of a kind which is produced when charged particles, mostly electrons, spiral very close to the speed of light, making tight helices around the magnetic field. So you have to have both these things, very energetic particles and the magnetic field. So that tells us both these things have to be present. In some cases, the techniques of very long baseline interferometry, where you connect radio telescopes around the world and in some cases in orbit, can show us that jets still act. In some cases, we can see the blobs moving outwards so fast that it must be, as we inferred, pushing right up against the speed of light. There's a connection with a lot of calculations of what happens near black holes, where even a small magnetic field could be twisted by the rapid motions in black holes to provide a natural way to propel a tiny amount of the material that would otherwise be moving its way in, eventually to fall in, and instead shoot it out close to the speed of light. If it weren't close to the speed of light, it would never get out for us to see it. And the jets can be extremely narrow. The magnetic field seems to have a role in keeping them that way, because some of them trace out very narrow cones, only a couple of degrees in width. And some of them can maintain their integrity for the better part of a million light years in oppositely directed beams. And these sorts of calculations tell you that when you have the jets, they should be coming from the poles of the inner accretion disk, material swirling around the black hole. And indeed, we can't see the accretion disk yet, What we can sometimes see, especially, for example, with data from Hubble, is a larger disk of material that should generally be lined up with the accretion disk stuff that hasn't gotten in that far yet. When we see that, that is perpendicular to the radio jets. These things are enormously energetic. Some galaxies manage to blow them out without all of the radiation that you expect coming out of a quasar.
Next question is, what are the different types of AGN and what are the differences between them?
As in a lot of things, we originally started labeling different kinds of AGN as we found them in different categories in different ways, and only later started to have the information to figure out which ones belong together. Our first hint that AGN were there goes back at least to 1918, when photographs taken with the Crosley telescope, which had been relocated from England to California, showed the jet in M87. But there was no context for that, so we really trace recognition that special things go on in the centers of galaxies to an examination of galaxy spectra done by Carl Seifert in the 1940s. He examined the spectra of all the galaxies that had good data at that time, which was only a few hundred, and where the data consisted of spectra recorded on tiny photographic plates, so he had to tour various observatories' archives. He found about a dozen that didn't fit with any ordinary pattern, but sort of formed a group to themselves that have since come to be known as Seifert galaxies. They showed very strong emission lines, hot gas, but the ratios of various emission lines didn't fit what you got with star-forming regions like the Orion Nebula. The gas had to be much more highly ionized, and the widths of the line said it was moving around much faster than in ordinary galaxies. A quarter of a century later, several groups around the world recognized that these in fact formed two subclasses that we come to call Type 1 and Type 2 Seiferts. In the Type 1 Seiferts, certain emission lines, the hydrogen lines, things that can be produced at high density, are enormously broad. Doppler shifts of 5,000 kilometers a second. And we now think these are the ones where we're looking right down to the material near the black hole. We see the stuff that's close, that's moving very fast. There's another type where all the emission lines have the same width. And a whole host of observations have led us to realize that at least some of the time, these two kinds of Seifert galaxy are the same thing, seen in different directions. That there's a lot of obscuring material outside the accretion disk. People sometimes talk about it as the torus, even though it doesn't have to be nearly that neat or that continuous. So in that case, we think observations lead us to see rather different things depending on how we look at the same structure.
This is the end of this part of the interview with Professor Bill Keel. However, you can continue listening to the interview on our next video. If you're reading this on the Witty Astronomers blog, the next video is just below. If you're on YouTube, you can click the link in the description.